September 1943. 25,000 feet above occupied France, an American P-51B Mustang encounters a Messerschmitt Bf-109G. The German pilot smiles. This is his altitude, his domain. Every Allied fighter he's faced here has struggled, gasped, and died. But today, something impossible happens. The Mustang doesn't just survive at this oxygen-starved height. It accelerates, it climbs, it dominates. The German pilot's last thought before his engine coughs and fails is simply, how? The answer to that question begins not in the skies over Europe, but in a metallurgy laboratory in Birmingham, England. And it involves one man's obsession with an alloy that everyone said was impossible to make. This is the story of how Leonard Bessemer Files' forbidden nickel alloy didn't just change aviation, it changed the outcome of World War II. To understand why this matters, we need to go back to 1940. Britain stood alone against Nazi Germany. The Battle of Britain raged in the skies, and while the Spitfire and Hurricane were magnificent aircraft, they had one critical weakness: altitude. Above 20,000 feet, their Merlin engines began to lose power. The superchargers that forced air into their engines at high altitude were literally destroying themselves. Here's the problem that nobody could solve. As aircraft climbed higher, the air got thinner. Less air meant less oxygen for combustion. Less combustion meant less power. The solution seemed simple. Use a supercharger, essentially a turbine that compresses thin, high-altitude air before it enters the engine. But there was a catch. The supercharger turbines spun at astronomical speeds, up to 40,000 revolutions per minute. At these speeds, the exhaust gases passing through the turbine reached temperatures exceeding 800 degrees Celsius. And here's where the nightmare began. Every metal alloy available in 1940 would fail at these conditions. Steel alloys would soften and deform. The turbine blades would stretch, warp, and eventually disintegrate. A supercharger might last 20 hours before catastrophic failure. For a fighter that needed to fly hundreds of combat missions, this was unacceptable. Engineers watched in frustration as blade after blade failed. They saw the metal actually creeping, slowly deforming under the constant stress and heat. Microscopic grain boundaries in the metal would slide past each other. Atoms would migrate. The crystal structure would collapse. And then, suddenly and catastrophically, the blade would fail. Often, it would fail in flight. The turbine would explode. Shrapnel would tear through the engine. Pilots died. The British Air Ministry issued an urgent classified directive. Find a metal that can survive these conditions, or we will lose the war in the stratosphere. German bombers were already operating at altitudes where British fighters struggled. If the Luftwaffe developed high-altitude fighters that British planes couldn't reach, the war would be over. This brings us to Leonard Bessemer File. And yes, that middle name is significant. He was the grandson of Henry Bessemer, the man who revolutionized steel production in the 19th century. Metallurgy was literally in his blood. By 1940, File was working at the Wigan Works in Birmingham, a facility owned by the International Nickel Company. His specialty was nickel alloys, and he had spent years studying how different elements affected metal properties at extreme temperatures. File understood something that most metallurgists of his time didn't fully appreciate. The problem wasn't just about finding a stronger metal. Strength at room temperature meant nothing. What mattered was creep resistance, the ability of a metal to resist deformation under prolonged stress at high temperatures. And this required a completely different approach to alloy design. He began with a base of nickel and chromium, the same foundation used in stainless steels. The nickel provided toughness and resistance to thermal fatigue. The chromium created a protective oxide layer that prevented the metal from burning away in the hot exhaust gases. But this alone wasn't enough. These alloys still crept at supercharger temperatures. File's breakthrough came from an unexpected direction. He started adding small amounts of titanium and aluminum to his nickel-chromium base. Now, this sounds simple in retrospect, but at the time, it was considered borderline impossible. Here's why. Titanium and aluminum are both extremely reactive metals. They would oxidize instantly when exposed to air during the melting process. They would combine with oxygen, nitrogen, and carbon, creating brittle compounds that would ruin the alloy. Every attempt to add these elements to molten nickel resulted in a useless, contaminated mess. This is why Fehl's alloy was considered forbidden. Not because it was classified, but because conventional metallurgical wisdom said it simply couldn't be manufactured. The chemical reactions involved were too violent, too uncontrollable. Senior metallurgists told Fehl he was wasting his time and precious wartime resources. But Fehl was Bessemer's grandson. He didn't accept the word impossible. What Fehl did next was genuinely revolutionary. He developed a vacuum melting process specifically for this alloy. Instead of melting the metals in air, he did it in a chamber evacuated of almost all atmosphere. Without oxygen present, the titanium and aluminum couldn't form unwanted compounds. They dissolved cleanly into the nickel matrix. But this created its own problems. Melting metal in a vacuum required completely new furnace designs. The crucibles had to withstand not just high temperatures, but the stress of operating in a near vacuum. Every seal had to be perfect. A single leak would ruin an entire batch. Fehl spent months developing the process. Batch after batch failed. The metal would still contain impurities. Or it would be too brittle. Or it would have the wrong crystal structure. The pressure was immense. By early 1941, the war was going badly. Germany had conquered most of Europe. The Soviet Union was reeling from Operation Barbarossa. The United States hadn't yet entered the war. Britain needed every technological advantage it could get. And then, in the spring of 1941, Fehl succeeded. He produced a nickel-chromium titanium-aluminum alloy that demonstrated unprecedented high-temperature properties. When tested under conditions simulating supercharger operation, the alloy showed minimal creep even after hundreds of hours. The titanium and aluminum had done something extraordinary at the atomic level. They had combined with nickel atoms to form tiny precipitates of a compound called gamma prime, Ni3Lti. These precipitates were only a few nanometers in size, far too small to see even with the optical microscopes of the time. But their effect was dramatic. Here's what made gamma prime so special. Unlike most precipitates, which make metals brittle, gamma prime actually strengthened the alloy in a unique way. The precipitates formed a three-dimensional network throughout the metal's crystal structure. When the metal tried to deform under stress, dislocations, the atomic scale defects that allow metals to bend, couldn't move easily through this network. The precipitates blocked them. But because the gamma prime phase was coherent with the surrounding nickel matrix, meaning the atomic spacing matched almost perfectly, the metal remained ductile. It was strong without being brittle. This was the holy grail of high-temperature metallurgy. Fehl called his alloy Mnemonic 80. The name came from Nickel Monel International Company. Though people liked to joke, it stood for nearly impossible metal on normal industrial conditions. The alloy contained roughly 80% nickel, 20% chromium, with small but critical amounts of titanium and aluminum. Getting the proportions exactly right had required hundreds of experiments. Too little titanium and aluminum, and there weren't enough gamma prime precipitates. Too much, and they would coalesce into large particles that made the alloy brittle. In June 1941, the first supercharger turbine blades made from Mnemonic 80 were installed in a developmental Merlin engine. The initial tests were nerve-wracking. Engineers fully expected the blades to fail, as all previous attempts had. They set up high-speed cameras to capture the moment of failure. They positioned the test stand behind blast walls in case of catastrophic explosion. They ran the engine at full power, simulating the conditions at 25,000 feet. 1 hour passed. Then 10 hours. Then 50 hours. The blades showed no signs of failure. No stretching, no warping, no creep. Engineers examined them under microscopes and couldn't find any deterioration. They ran the test to 100 hours, then 200. The mnemonic 80 blades performed flawlessly. For the first time in aviation history, a supercharger turbine could reliably sustain the conditions needed for high-altitude flight. But having a material that worked was only half the battle. Mnemonic 80 was extraordinarily difficult to manufacture. The vacuum melting process was slow and expensive. Each furnace could produce only small batches. The alloy was also incredibly hard to machine. It work hardened rapidly, meaning that as cutting tools tried to shape it, the metal would become progressively harder, dulling the tools. Conventional machining methods would destroy expensive tungsten carbide cutting tools in minutes. New techniques had to be developed. Grinding replaced traditional cutting. Electrical discharge machining was pioneered specifically to work with mnemonic 80. Then there was forging the turbine blades. Mnemonic 80 had to be formed at precise temperatures. Too cold, and it would crack. Too hot, and the carefully engineered microstructure would be destroyed. The blades had complex curved shapes optimized for aerodynamic efficiency. Creating these shapes from a material that resisted deformation was a manufacturing nightmare. Specialized forging dies had to be designed. New heat treatment protocols had to be developed. Workers needed extensive training. Every blade had to be individually inspected, using X-ray radiography, itself a relatively new technology, to ensure there were no internal defects. The British government classified everything about mnemonic 80 at the highest level. The alloy's composition was a state secret. The manufacturing process was a state secret. Even the fact that a new supercharger alloy existed was classified. Workers at the Wigan Works and Rolls-Royce facilities worked behind triple security checkpoints. They couldn't discuss what they did with their families. Documents about the alloy were stamped most secret, higher than top secret, because it indicated the information was critical to the war effort. Meanwhile, at Rolls-Royce, a brilliant aerodynamicist named Stanley Hooker was working on his own revolution, the two-stage supercharger. Hooker had joined Rolls-Royce in 1938, and he immediately recognized that the single-stage superchargers used in early Merlin engines were fundamentally limited. A single-stage supercharger could compress air by a certain ratio, but at high altitudes, this wasn't enough. You needed more compression. The obvious solution was to use two supercharger stages in series. The first stage would compress the air, then the second stage would compress it further. But every previous attempt at two-stage supercharging had failed for two reasons. First, compressing air heats it up dramatically. After the first stage of compression, the air would be so hot that compressing it further would cause detonation in the engine cylinders. Essentially, the fuel-air mixture would explode prematurely, destroying the engine. Second, two-stage superchargers required turbines that were even more highly stressed than single-stage units. No available material could survive the conditions. Hooker solved the first problem with an intercooler, a radiator that cooled the air between the first and second compression stages. This was engineering brilliance in itself, because the intercooler had to be compact enough to fit in an aircraft while being efficient enough to cool air that was already extremely hot. Hooker's design routed the compressed air through a maze of thin tubes surrounded by coolant. The air temperature dropped from over 150 degrees Celsius to near ambient temperature. This cooled air could be compressed again without causing detonation, but the intercooler was useless without solving the second problem: the turbine blades. And this is where Field's mnemonic 80 entered the picture. When Hooker learned in late 1941 that Rolls-Royce now had access to a material that could survive two-stage supercharger conditions, he immediately redesigned the entire system around it. The result was the Merlin 60 series engine, and it was a quantum leap in performance. A standard Merlin engine produced about 1,200 horsepower at sea level. At 20,000 feet, this dropped to around 800 horsepower. At 25,000 feet, barely 600. But the Merlin 61 with its two-stage supercharger and mnemonic 80 turbine blades, produced over 1,400 horsepower at sea level, and still generated over 1,000 horsepower at 25,000 feet. At 30,000 feet, where earlier Merlins were gasping, the Merlin 61 still put out nearly 900 horsepower. This was game-changing performance. The first aircraft to receive the two-stage Merlin was the Spitfire. The Spitfire Mark IX, equipped with the Merlin 61, entered service in July 1942. Pilots couldn't believe the difference. One RAF pilot reported, "Below 20,000 feet, the Mark IX felt like a normal Spitfire. But above that altitude, it was like someone had strapped a rocket to the aircraft. We could climb to 30,000 feet and still have power to spare." German fighters that tried to escape by climbing suddenly found us following them up, and we were faster. The Luftwaffe was stunned. Their Bf-109F and early G models had dominated high-altitude combat for years. German fighters would climb above 25,000 feet, where they knew British fighters struggled, and bounce unsuspecting Allied aircraft from above. Suddenly, this tactic stopped working. Spitfire Mark IXs could meet them at altitude and outperform them. German intelligence reports from late 1942 express bewilderment about how British fighters had suddenly gained so much high-altitude capability. But the Spitfire Mark IX was just the beginning. In October 1942, the United States Army Air Forces made a decision that would change the course of the air war over Europe. They decided to install the Packard V-1650, the American license-built version of the two-stage Merlin in the North American P-51 Mustang. The Mustang had been developed as a long-range escort fighter, but it had a critical flaw. Its original Allison V-1710 engine used a single-stage supercharger and performed poorly above 15,000 feet. The aircraft was relegated to low-altitude tactical reconnaissance and ground attack roles. It was a beautiful airplane, sleek, aerodynamic, with excellent range, but it couldn't fight at the altitudes where bombers needed protection. When test pilot Bob Chilton first flew a Mustang equipped with the Packard V-1650 Merlin in October 1942, he landed and immediately told engineers, "This changes everything. We've just built the best fighter in the world." He wasn't exaggerating. The P-51B, as the Merlin-powered Mustang was designated, combined the Mustang's aerodynamic efficiency and long range with the Merlin's high-altitude power. The result was a fighter that could escort bombers all the way to Berlin and back, something no other Allied fighter could do, while outperforming German fighters at any altitude. Inside those Packard Merlins, spinning at 40,000 RPM in superheated exhaust gases, were turbine blades made from mnemonic 80. American metallurgists at Packard had been given access to the alloy's specifications under the Lend-Lease agreement, though they didn't initially understand why this particular alloy was so critical. They soon learned. Early attempts to substitute American alloys failed spectacularly. The substitute blades would last 30 to 50 hours before failure. Only mnemonic 80, produced under File's vacuum melting process, could survive. Packard had to set up an entirely new production line just for the supercharger turbines. They imported British experts to train American metallurgists. They built specialized vacuum furnaces based on Fiel's designs. They developed new quality control procedures because a single defective blade could destroy an entire engine. By mid-1943, Packard was producing thousands of Merlin engines per month, and every single one contained mnemonic 80 turbine blades. December 1943. The 8th Air Force launches a massive bombing raid against Schweinfurt, Germany, a target deep in the heart of the Reich. Previous raids on Schweinfurt had been catastrophic disasters. Without long-range escort, B-17 and B-24 bombers had been massacred by German fighters. The October 1943 Schweinfurt raid lost 60 B-17s out of 291 dispatched, a 20% loss rate that was utterly unsustainable. But this December raid is different. For the first time, P-51B Mustangs escort the bombers all the way to the target and back. The bombers fly at 25,000 feet. The Mustangs fly cover at 30,000 feet. When Luftwaffe fighters try to attack, the Mustangs dive on them from above. German pilots are shocked to encounter American fighters this deep into Germany, and even more shocked that these fighters are outperforming their own aircraft at high altitude. A Bf-109G pilot might have 1,200 horsepower at 30,000 feet. The P-51B has 1,400. The German fighter might climb at 1,500 feet per minute at this altitude. The Mustang climbs at over 2,000 feet per minute. In a diving attack, the Mustang reaches speeds that the 109 can't match. And when the fight gets turning, the Mustang's superior power-to-weight ratio at altitude gives it an edge in sustained turns. The German pilot's only advantage, experience, isn't enough to overcome the enormous performance gap. Major Don Blakesley, commanding officer of the 4th Fighter Group, described it like this: "Above 25,000 feet, we owned the sky. The Germans would try to climb away from us, and we'd just follow them up. They'd try to dive away, and we'd catch them. Some of them tried to fight, and that usually ended badly for them." The P-51 at altitude was just unbeatable. The impact on the bomber offensive was immediate and dramatic. In the months before long-range escort fighters, the 8th Air Force was losing bombers at rates approaching 10% per mission. After P-51s began escorting in numbers, loss rates dropped below 2%. German fighter units that had been decimating bomber formations suddenly found themselves fighting for survival. By early 1944, the Luftwaffe was effectively losing the air superiority battle over its own territory. And none of this would have been possible without Leonard Bessemer Field's forbidden alloy. Every one of those Mustangs and Spitfires fighting at altitude was sustained by mnemonic 80 turbine blades. Those tiny pieces of carefully engineered metal, spinning in superheated exhaust, invisible to everyone except the engineers who designed them, were the critical enabling technology. Without them, the superchargers would fail. Without superchargers, the engines would be powerless at altitude. Without high-altitude power, the fighters couldn't escort the bombers. Without escort, the bomber offensive would fail. Without air superiority, D-Day would be impossible. It's worth pausing here to understand exactly what was happening inside those turbine blades at a microscopic level, because the science is genuinely fascinating. When a mnemonic 80 blade operated at supercharger conditions, spinning at 40,000 RPM in 800-degree exhaust gas, it was subjected to stresses that would liquefy ordinary steel. The centrifugal force alone created tensile stresses exceeding 50,000 pounds per square inch. The temperature was high enough that atoms in the metal had significant thermal energy and wanted to move around. In a conventional alloy, this combination of stress and temperature would cause catastrophic creep. The metal's grain boundaries, the interfaces between different crystal regions, would act as weak points. Atoms would migrate along these boundaries. Vacancies and dislocations would accumulate. The grain boundaries would slide past each other. The blade would stretch. Eventually, it would fail. But mnemonic 80's microstructure was different. The gamma prime precipitates created by the titanium and aluminum served multiple functions. First, they pinned dislocations, the linear defects in the crystal structure that allow plastic deformation. When a dislocation tried to move through the metal, it would encounter a gamma prime precipitate and get stuck. This dramatically reduced the rate of deformation. Second, the precipitates inhibited grain boundary sliding. The gamma prime particles would form along grain boundaries, essentially riveting adjacent grains together. This prevented the boundaries from acting as planes of weakness. Third, and most remarkably, gamma prime actually got stronger at elevated temperatures. Most strengthening mechanisms in metals become less effective as temperature increases. But gamma prime's ordered crystal structure became more resistant to dislocation movement at higher temperatures. The alloy was literally optimized. for exactly the conditions it would face in operation. File didn't fully understand this microscopy when he developed the alloy. The detailed science of gamma prime strengthening wouldn't be worked out until the 1950s and 60s, long after the war. But through careful experimentation and testing, he had empirically discovered the right combination of elements and processing to create the microstructure needed. This is a recurring theme in materials science. Sometimes the engineering precedes the fundamental understanding. By mid-1944, the Allies had overwhelming air superiority over Europe. German fighter production had actually increased. The Luftwaffe was building more aircraft than ever, but they were being shot down faster than they could be replaced. Experienced German pilots were dying or being captured. Replacements had minimal training and were thrown into combat against Allied pilots who had every technological advantage. At the Tehran Conference in November 1943, when Stalin met with Roosevelt and Churchill for the first time, the Soviet leader was briefed on Allied air operations. When he learned about the long-range fighter escorts and their high-altitude performance, he immediately recognized the strategic significance. He told Roosevelt, "These new fighters of yours, they are more valuable than a dozen infantry divisions. They mean Germany cannot hide its industry anywhere. You can reach any target, and your bombers will come home." Stalin wasn't wrong. The combination of long-range escort fighters and high-altitude capability meant the Allies could conduct precision daylight bombing of German industry, while the RAF continued area bombing by night. Germany's industrial capacity was systematically destroyed. Oil refineries, ball-bearing plants, aircraft factories, all were hit repeatedly. The Luftwaffe was ground down not just in combat, but by the destruction of its logistics and production base. And underpinning all of this, the entire strategic bombing campaign, the achievement of air superiority, the preparation for D-Day, were those turbine blades. Thousands upon thousands of mnemonic 80 turbine blades, each one a small masterpiece of metallurgical engineering, each one essential to the function of the superchargers that gave Allied fighters their decisive advantage. After the war, when the full story of Allied technological developments became public, the significance of materials science in determining the war's outcome became clear. The Manhattan Project and the atomic bomb captured public imagination, but metallurgists understood that more subtle innovations had been equally important. Mnemonic 80 was one of these. It didn't produce a dramatic mushroom cloud. It didn't sink battleships or destroy cities. But it enabled a capability, sustained high-altitude fighter operations that the Axis powers couldn't match. German metallurgists were aware they needed better supercharger materials. They experimented with various alloys, including some that contained similar elements to mnemonic 80. But they never developed an equivalent vacuum melting process. German turbine blades were made from cobalt-based alloys that had inferior high-temperature properties. The blades would last long enough for the engine to pass acceptance testing, but they degraded rapidly in service. Luftwaffe maintenance reports from 1943-45 are full of references to supercharger failures and reduced high-altitude performance. Some historians have speculated what might have happened if Germany had developed an equivalent to mnemonic 80. Could the Bf-109G or FW-190D have matched the Mustang at altitude? Could German jets like the Me-262 have been even more effective? These are counterfactuals, but they highlight an important point. The war was won and lost, not just in battles, but in laboratories and factories. The side with better materials, science, better manufacturing processes, and better engineers had an overwhelming advantage. Leonard Bessemer Feil continued working in metallurgy after the war. He never sought publicity for his wartime work. Most of it remained classified well into the 1950s. He died in 1969, and his obituaries focused on his peacetime contributions to materials science. But among metallurgists and aerospace engineers, Feil is remembered as the man who solved one of the Second World War's most critical materials problems. The legacy of mnemonic 80 extends Far beyond World War II, the alloy and its descendants became the foundation of the entire field of nickel-based superalloys, modern jet engines, the turbofans that power commercial aircraft, the engines in military fighters, the gas turbines in power plants, all use direct descendants of Field's original alloy. Engineers have refined the composition, adding elements like rhenium, ruthenium, and hafnium to push high-temperature performance even higher. They've developed single-crystal casting techniques to eliminate boundaries entirely. They've created ceramic coatings that allow turbine blades to operate at temperatures that would melt the underlying metal. But the fundamental principle remains the same: nickel-chromium base, strengthened with gamma-prime precipitates formed by carefully controlled additions of aluminum and titanium. Every modern turbine engine contains the ghost of Field's 1941 innovation. When you board a commercial airliner, you're trusting your life to technology that descends directly from that forbidden alloy. There's a broader lesson here about technological development during wartime. The Manhattan Project cost $2 billion and employed 130,000 people. By contrast, the entire development of Mnemonic 80, from Field's initial experiments through scaled production, cost perhaps a few million pounds and employed a few hundred people. Yet the strategic impact was arguably comparable. The atomic bombs ended the war with Japan, but they were dropped from B-29s that flew to their targets escorted by fighters with supercharged engines. Everything was connected. Modern materials science still follows the path that Field pioneered. We still develop new alloys by carefully balancing multiple elements to create favorable microstructures. We still use vacuum or inert atmosphere processing for reactive materials. We still test and iterate until we find combinations that work. The tools have improved. We can now model atomic-scale interactions with computers, observe microstructures with electron microscopes, and test materials under precisely controlled conditions. But the fundamental process of materials development hasn't changed as much as you might think. So let's return to that September 1943 encounter over France that we started with. The American P-51 pilot, who outflew the Messerschmitt, didn't know Leonard Bessemer Field's name. He'd never heard of Mnemonic 80. He probably couldn't have told you exactly how a two-stage supercharger worked. But when he advanced his throttle at 25,000 feet and felt his Merlin respond with smooth, sustained power, he was benefiting from Field's breakthrough. When he climbed through 30,000 feet pursuing a German fighter that was struggling at that altitude, the turbine blades in his supercharger were performing exactly as Field had designed them to, surviving conditions that would have destroyed any previous material. The German pilot, plunging toward the Earth with his engine failing, might have wondered what had gone wrong. His aircraft was well designed. His engine was sophisticated. He was an experienced pilot, but he'd been beaten by an enemy with a fundamental technological advantage. His supercharger was working at the limits of its material's capability. The Mustang's supercharger was operating well within its design envelope, thanks to turbine blades made from an alloy that his side couldn't produce. This is how wars are won and lost. Not always by the most dramatic weapons or the most charismatic leaders, but sometimes by metallurgists in laboratories, solving problems that most people never know existed. Field's forbidden alloy let Mustangs outrun Messerschmitts at altitude, because it solved a problem at the atomic level, the problem of how to make metal survive extreme conditions. That solution cascaded upward through scales, from atoms to microstructures, from microstructures to turbine blades, from turbine blades to superchargers, from superchargers to engines, from engines to aircraft, from aircraft, air superiority, from air superiority to victory. In the end, World War II was won by many things: courage, leadership, industrial capacity, intelligence, but also by a man named Leonard Bessemer Field, who looked at a problem everyone said was impossible and decided to solve it anyway. His alloy, literally forged in vacuum from forbidden materials, gave Allied pilots the ability to fight at altitudes where the enemy couldn't follow. And that made all the difference. The next time you see a P-51 Mustang at an air show, or watch one in a documentary, remember, inside that engine, even if it's been restored with modern parts, the design still carries the legacy of those mnemonic 80 turbine blades. The same blades that spun at 40,000 RPM in superheated exhaust over Berlin and Tokyo. The same blades that gave a generation of Allied pilots the power they needed when they needed it most. The same blades that helped win the most important war in human history. That's the story of how one metallurgist's forbidden alloy let Mustangs outrun Messerschmitts at altitude. It's a story about materials science. It's a story about engineering under pressure. But most of all, it's a story about how small innovations, applied at the right time and place, can change the world.